concept in a stochastic process or in Monte Carlo solutions is the random walk, RW, random walk. And random walk is a Markov chain type, a Markov chain type path. So it is a path trajectory of something, because we say random walk. When someone starts to walk, you can specify the trajectory of the random walk. So this is a Markov chain type path that consists of random steps. For example, again, let's go back to my example of students in class. These points here are students. I start asking questions from this guy here, and he or she says that the next student is this one. So this is the path from the first student to the next one. And continue this random process. The next student, this one, this one, this one. This is a random traveling from the first student to the last one, randomly. So we have a Markov chain events, which is the label of the students or the name of students. And the path of this Markov chain traveling or Markov chain journey from the first one to the last one is called the random walk process. Two well-known examples of the random walk are the Levy flight, and the Brownian motion in diffusion of heat, diffusion of momentum, or diffusion of mass. So I don't want to speak about these processes because they are somehow physical, but a random motion of particles in a fluid is called the Brownian motion. For example, consider a dust particle, small dust particle moving in there. If you focus on it, you will see that the motion of dust particle is somehow random because of random collision of air particles adjacent to that dust particle. The motion of the dust particle is also random. So you can see the Brownian motion here, but if you inject, for example, a drop of ink into the water, you can see the Brownian motion or the random motion of water particles. So we are trying to mimic the Brownian motion, but the Brownian motion is about the particles. So particles are very, very small part of a substance. So, but here we, the distance between 2 points in space is not infinitesimal, is not differential. So when the distance between 2 points in space goes to 0, this random walk process goes to the Brownian motion. And also the other point here is that the Brownian motion is the dominant process in diffusion problems, diffusion of heat, mass, or momentum. And again, you know that the partial differential equations resulting from the diffusion of different process is parabolic or elliptic. So this kind of solution, Monte Carlo solution for a partial differential equation can be used for the solution of parabolic and elliptic equations. There are some corrections or modifications for hyperbolic equations, which contain some sharp discontinuities, such as the Berger's equation or shock waves. But here in this video, I'm speaking about the Monte Carlo solution of the parabolic or elliptic equations, partial differential equations, based on the random walk concept. The other point here is the ergodic process. You know that the Brownian motion, based on the concept ergodic process in statistics, the Brownian motion and also the Levy flight are both ergodic processes. And here, the random walk process also should be an ergodic process. Okay, this is the classification of Monte Carlo methods for the solution of parabolic and elliptic equations. This is the Markov chain concept, and this one is the random walk concept. Based on these concepts, I can introduce the algorithm of the Monte Carlo method for the solution of partial differential equations. But before that, let's speak about the advantages and disadvantages of the Monte Carlo method. Is used to compute the value of the unknown function at each point in space or position and time, independent of other positions and time. This is the main advantages of the Monte Carlo method for the solution of partial differential equation. You know, when you discretize a partial differential equation using finite element method, finite volume method, or any other numerical method, you have many unknown functions and in grid space, in grid points in space, and you have to solve a set of equations or a system of algebraic equations simultaneously. So, if you want to compute the temperature at a point and at a particular point in space, you have to also compute the temperature of other points, and this system of equations simultaneously converge to the solution. But consider that you just want to compute the temperature at a specific point in space. You don't need to compute the temperature of other points, or even at other times. I am planning to just compute the temperature at a specific point and a specific time. In this case, the best choice for you is the Monte Carlo method. So, computing the value of the unknown function at each x vector means the position vector and time independent of other positions and times. This strategy is well appropriate for inverse heat transfer problems. So, if you are trying to solve an inverse ill-posed, of course, heat transfer, the numerical, the Monte Carlo is a good choice for you as your numerical method. And no need to the system of equations. This is called the point value. So if you want to compute the point value of the unknown function, the best numerical method is the Monte Carlo method. And the other advantage of the Monte Carlo method is no sensitivity to dimension. It means that you can easily extend your code, your numerical code, to three-dimensional geometries, and you're from one-dimensional to two-dimensional. But you know it's somehow difficult in other numerical methods to develop a one-dimensional code for two-dimensional cases or three-dimensional cases. But no sensitivity to dimensional geometry. The other advantage is low memory of a computer and also and even time. If you want to compute the temperature at a point, you can easily use the Monte Carlo method with very low computational time. But if you want to compute the total times and total points in space, it's maybe expensive. The Monte Carlo method may be expensive. But if you're targeting a point in space at a specific time, the best choice with the lowest computational cost is the Monte Carlo method. And also, similar to other Monte Carlo algorithms, the MC method is well appropriate for parallel processing systems, because the computations can be done separately, and you can separate computations, and you can simultaneously perform the random walk starting from points in space using different cores, and tremendously and remarkably reduce the computational cost by using the parallel processing. For example, here in our example of students in class, I can ask my colleague to come to the class, and simultaneously we can ask questions from different students in class, 3 questions at a time. So the main advantage of the Monte Carlo method is its flexibility for parallel processing programming.